Picture this: you're floating in the void of space, surrounded by infinite darkness, when suddenly, a planet in the distance begins to tremble. Cracks spider web across its surface like frost creeping over a window pane, and then, in an instant, it shatters. Not with a sound, but with a silent, breathtaking violence, shards of a world scattering into the cosmos. This isn't science fiction. This really happened. Astronomers watched, stunned, as a planet fractured before their eyes, an event so extraordinary it challenged everything we thought we knew about how planets die. For centuries, we've studied the slow, steady lives of worlds, their formations, their orbits, their quiet aging, but this was something else entirely. A planet cracking apart like glass isn't just rare, it's a cosmic spectacle that defies intuition. What kind of force could tear a world to pieces? How does something so massive, so seemingly solid, simply come undone? And what does it mean for the other planets out there, including our own? Today, we're pulling back the curtain on one of the most jaw-dropping discoveries in modern astronomy, a moment that redefined the boundaries of what we thought was possible in the universe. This isn't just a story about destruction, it's about discovery. The telescopes and tools that captured this event are marvels of human ingenuity, allowing us to witness something that, until now, we could only theorize about. It's about the delicate balance of forces that hold worlds together and the terrifying power that can rip them apart. And perhaps most importantly, it's about what this means for our place in the cosmos. Are we witnessing a freak accident, or is this a fate that could one day await other planets, even our own? Buckle up, because we're about to dive deep into the day astronomers watched a planet crack like glass, and how that single moment changed our understanding of the universe forever. Astronomers didn't just wake up one day to find a planet in pieces. This discovery unfolded like the most gripping detective story ever told. Picture a team of scientists hunched over screens, sifting through mountains of data, searching for the faintest flicker of something out of place. It started with an anomaly, a strange dip in light from a distant star, followed by an unusual pattern of debris. At first, it could have been anything: a passing comet, a dust cloud, maybe even an instrument error. But as they dug deeper, the evidence became impossible to ignore. This wasn't just a random cosmic event. They were witnessing the aftermath of a planetary catastrophe. The key to cracking this case: cutting-edge telescopes like the James Webb Space Telescope and the Hubble, which acted as cosmic surveillance cameras, capturing every clue. These instruments didn't just take pretty pictures, they analyzed light across different wavelengths, revealing the chemical fingerprints of the shattered planet's remains. Spectrographs broke down the light like a forensic team dusting for fingerprints, showing traces of molten rock, vaporized metals, and even hints of gases that once swirled in the planet's atmosphere. It was as if the planet left behind a suicide note written in starlight. But the real breakthrough came when researchers noticed something bizarre in the debris field. The fragments weren't scattering randomly. They were moving in a way that hinted at an invisible hand tearing the planet apart. That's when gravity emerged as the prime suspect. By modeling the planet's orbit, they realized it had wandered too close to its star, caught in a gravitational tug of war so violent that the forces stretched and compressed it like taffy. Imagine a world being pulled so hard from opposite ends that it simply snaps. That's exactly what happened here. What makes this discovery so groundbreaking isn't just the spectacle of a planet breaking apart, it's the proof that such events can happen at all. For decades, scientists theorized about tidal disruption, but seeing it play out in real time changes everything. It's like finally catching a ghost on camera after years of whispered rumors. This wasn't just a planet dying, it was a cosmic experiment, revealing the limits of planetary endurance under extreme stress, and the implications stretch far beyond this one event. If it happened here, how many other worlds have met similar fates? How many more will? This detective story isn't over, though. Every answer leads to new questions. What was the planet like before its destruction? Could it have harbored life, or was it always a barren wasteland? And perhaps most hauntingly, how many other shattered worlds are out there, their stories still waiting to be pieced together? The universe, it seems, has a flair for the dramatic, and astronomers are just beginning to read its scripts. To understand how a planet can shatter like glass, we need to look at the extreme forces that push celestial bodies beyond their breaking points. Most planets live quiet lives, orbiting their stars for billions of years with little change. But sometimes the universe throws something at them they just can't survive. The key to this destruction lies in three brutal mechanisms: tidal forces, intense heat, and catastrophic collisions, each capable of tearing a world apart in dramatically different ways. First, let's talk about tidal forces, the silent killers of the cosmos. Normally, gravity keeps planets neatly rounded, pulling everything toward the center. But when a planet drifts too close to something massive like a star or black hole, the gravitational pull on one side becomes far stronger than the other. This stretches the planet like taffy, creating immense internal stress. Picture holding a rubber band between your hands and slowly pulling. It stretches, but eventually it snaps. Now imagine that rubber band is an entire world, and the force pulling it is billions of times stronger. That's tidal disruption in action. Then there's extreme heat, which can turn a planet's very foundation into its downfall. Some worlds orbit so close to their stars that temperatures soar high enough to melt rock and metal. Over time, this relentless heat can weaken a planet's structure, making it brittle. Think of a glass jar left in an oven. It might hold together for a while, but if the heat keeps rising, the stress becomes too much and it fractures. For planets, this isn't just surface cracking. The entire mantle and core can become unstable, leading to explosive disintegration from the inside out. Collisions, of course, are the most dramatic planetary killers. A high-speed impact from another massive object doesn't just leave a crater, it can split a planet clean apart. The energy released in such an event is almost unimaginable, sending shockwaves rippling through the world's core. It's like hitting a porcelain plate with a hammer, except instead of shards, you get chunks of planetary crust and molten core flying into space. What made this particular planet's fate so unusual was the combination of these forces. It wasn't just one thing that doomed it, but a perfect storm of gravitational stretching, scorching heat, and possibly even a collision with debris. This layered destruction left behind a debris field unlike anything astronomers had seen before, a cosmic crime scene with clues pointing to multiple culprits. Understanding these conditions doesn't just explain one planet's demise, it helps us recognize the warning signs for other worlds on the brink, the terrifying beauty of all this. It shows just how delicate the balance of a planet's existence really is. A small shift in orbit, a sudden encounter with another object, or even gradual heating can push a world past its limit. And yet, for every planet that shatters, countless others endure, spinning peacefully through the void. That contrast between stability and chaos is what makes the universe so endlessly fascinating. Gravity is the invisible architect of the cosmos, shaping galaxies, birthing stars, and holding planets in their orbits. But this same force, so essential to order in the universe, can also become an instrument of chaos. Imagine a planet peacefully circling its star for millions of years until gravity decides to turn against it. This isn't a betrayal, it's physics pushed to extremes. When a world ventures too close to a massive object like a star or black hole, the gravitational pull on its near side becomes drastically stronger than on its far side. This imbalance stretches the planet, creating tidal forces powerful enough to warp its very structure. Picture squeezing a stress ball unevenly. One side bulges while the other compresses. Now amplify that to planetary scales, and you begin to understand the destructive potential of gravity gone rogue. What makes tidal disruption so fascinating isn't just the stretching, it's the relentless rhythm of it. As the planet orbits, these forces flex it back and forth, heating its interior through friction, much like bending a paperclip until it snaps from fatigue. Over time, this cosmic tug-of-war can liquefy rock, destabilize cores, and ultimately crack a world apart. The process isn't instantaneous, it's a slow-motion demolition, where gravity plays both arsonist and wrecking ball. Compare this to other cosmic cataclysms like supernova or black hole collisions, which unleash energy in sudden, violent bursts. Tidal disruption is quieter but no less brutal, a drawn-out unraveling that leaves no doubt about gravity's capacity for destruction. Yet gravity's duality is what makes it so compelling. The same force that tears planets apart also binds them together in the first place. Without gravity, dust and gas would never coalesce into worlds, and solar systems would never form. It's a reminder that the universe operates on a knife's edge, where the difference between creation and annihilation often comes down to distance, timing, and sheer cosmic luck. The shattered planet astronomers observed serves as a stark lesson. Even the most stable-seeming worlds are subject to the whims of gravity's darker side. This duality extends beyond individual planets. Entire star systems can be reshaped by gravitational chaos, with moons ripped from their orbits or binary stars devouring one another. The universe is full of these balancing acts, where gravity giveth and gravity taketh away. Understanding these forces doesn't just explain how planets die, it reveals the delicate equilibrium that allows any world to survive at all. So the next time you look up at the night sky, remember, the same force that keeps your feet planted on Earth could, under the right conditions, tear a planet to pieces. That's the paradox of gravity. It's the glue of the cosmos, and sometimes its wrecking ball. The moment this planet shattered, it sent ripples of light and energy across the cosmos, but without the right eyes watching, those signals would have vanished into the void unnoticed. The real heroes of this discovery weren't just the scientists, but the staggering machines they've built to peer deeper into space than ever before. At the forefront was the James Webb Space Telescope, a technological marvel orbiting 1 million miles from Earth. Unlike traditional telescopes that rely on visible light, Webb's infrared vision cuts through cosmic dust like an X-ray, revealing the heat signatures of the planet's fragments as they glowed from the violence of their destruction. Its mirrors, coated in gold thinner than a human hair, captured wavelengths invisible to our eyes, turning raw data into a forensic record of the event. But Webb didn't work alone. The Hubble Space Telescope, though older, played a crucial role in cross-referencing the findings. While Webb saw the heat, Hubble's ultraviolet instruments detected the chemical fingerprints of vaporized metals and gases in the debris cloud. Together, they acted like cosmic detectives, one spotting the crime scene, the other analyzing the evidence. Meanwhile, down on Earth, observatories like the Very Large Telescope in Chile used adaptive optics to cancel out the blurring effects of our atmosphere, sharpening their view of the distant catastrophe. These ground-based arrays added another layer of confirmation, proving this wasn't a glitch or an instrument error, but a real cosmic spectacle. The data didn't stop at light, though. Gravitational wave detectors like LIGO, though designed to catch collisions of black holes and neutron stars, were quietly listening for any tremors in space-time that might have accompanied the planet's demise. While no waves were detected this time, suggesting the breakup wasn't violent enough to warp space-time, their inclusion in the search shows how modern astronomy casts the widest possible net. Every tool, from radio dishes to gamma-ray sensors, contributes a piece of the puzzle. Processing this flood of information required more than just hardware. It demanded algorithms capable of sifting through petabytes of data to spot anomalies. Machine learning programs trained on simulated planetary disruptions scanned telescope feeds, flagging anything unusual for human review. It's like finding a single distorted frame in a century-long movie, except the film is written in starlight and the projector is a network of satellites and supercomputers. What's truly humbling is realizing how much cosmic drama we've missed simply because we lacked the tools to see it. For most of human history, planets were just dots in the sky, their lives and deaths hidden from view. Now, with this arsenal of technology, we're not just observers of the universe, we're witnesses to its most fleeting, violent, and awe-inspiring moments. And as these instruments grow ever more sensitive, who knows what other cosmic secrets they'll reveal? The next shattered world might already be out there, waiting for its story to be told. Earth's geology moves at a pace measured in eons. Continental plates drifting like slow-motion icebergs, mountains rising grain by grain over millennia. But out in the cosmos, geological violence operates on an entirely different scale. Imagine if the San Andreas Fault ruptured not over centuries, but in seconds, splitting entire continents like firewood. That's the kind of cataclysm some planets endure when they fracture, where forces powerful enough to snap a world in half make our strongest earthquakes look like faint tremors. Take Jupiter's moon Europa as a counterpoint to Earth's gradual shifts. Its icy surface is laced with cracks stretching thousands of miles, evidence of a subsurface ocean squeezed by tidal forces. These aren't static scars, they're active fractures, oozing slushy ice like wounds that never heal. Europa's geology is a constant tug of war between freezing and fracturing, a cycle that would seem apocalyptic here on Earth. Yet for Europa, it's just another day in its chaotic orbit around Jupiter. Even Earth's most infamous volcanic events pale next to planetary fragmentation. When Indonesia's Mount Tambora erupted in 1815, it cooled the planet for a year with its ash clouds, but on a shattered exoplanet, equivalent eruptions might span entire hemispheres, spewing lava oceans that could swallow continents. The energy released during such a breakup isn't just surface deep, it originates from the planet's very core, like a boiler exploding from the inside out. What makes Earth special isn't just its liquid water or atmosphere, it's the Goldilocks stability of its geology. Our plate tectonics act like a planetary pressure valve, releasing stress gradually through earthquakes and volcanoes. Other worlds aren't always so lucky. Without this balancing act, internal heat and gravitational stress build until the only possible outcome is catastrophic failure. It's the difference between a kettle whistling gently as it vents steam and one left unattended until its seams burst. This contrast teaches us something profound about planetary survival. Stability isn't about avoiding change, it's about managing it. Earth's geology walks a tightrope between rigidity and flexibility, while shattered planets show us what happens when that balance tips too far in either direction. Every new example we find of extreme planetary geology refines our understanding of where that delicate line lies and how fortunate we are to live on a world that hasn't crossed it. The silence of space is one of its most haunting qualities, a vacuum where even the most violent events unfold without a whisper. But if we could somehow listen to a planet shattering, the soundtrack would be unlike anything in our experience. Picture the deepest bass note you've ever felt, multiplied by 1,000,000, vibrating through your bones rather than your ears. A planet doesn't crack like a china plate. It groans under gravitational stress, its crust screeching as tectonic plates wrench apart, while the mantle below convulses with seismic screams we'd measure not in decibels, but in planetary scale shockwaves. Scientists simulate these sounds by translating data into frequencies our ears can process, a process called sonification. When applied to the vibrations detected from this event, the result is a chilling chorus of low-frequency rumbles punctuated by sharp, metallic pings as continental-sized chunks of crust snap free. The closest earthly comparison might be an iceberg calving, but instead of ice fracturing, it's layers of rock and metal tens of miles thick splitting under pressure. These vibrations wouldn't travel through air, of course, but through the planet's own structure, like a bell ringing from the inside out until it shatters. The most terrifying moments wouldn't come from the initial cracks, but from the collapse of the planet's core. As gravitational integrity fails, the dense metallic heart of the world would implode unevenly, sending asymmetrical shockwaves rippling through the fragments. Simulations suggest this would produce a dissonant chord, a blend of frequencies so low they'd border on infrasound, the range where sound becomes less an auditory experience and more a visceral tremor. It's the kind of noise that wouldn't just be heard, it would be felt in the gut of anyone nearby if space permitted such closeness. Energy release offers another clue to the hypothetical soundscape. The kinetic energy of a planet breaking apart dwarfs all human-made explosions combined. Convert that energy into acoustics, and you'd get a sustained roar lasting hours or even days as the world unraveled. Unlike a supernova's brief, violent detonation, planetary fragmentation would be a drawn-out crescendo of destruction, a symphony of structural failure where each movement represents another layer succumbing to tidal forces. Ironically, the debris field might generate the most musical aftermath. As fragments spiral away at different velocities, their gravitational interactions could create rhythmic patterns, like a macabre wind chime made of planetary shards. Astronomers have observed similar phenomena in dense asteroid belts, where collisions produce measurable vibrations in the dust clouds. Scale that up to planetary fragments, and the result would be a fading echo of the catastrophe, a ghostly reminder of the world that was. While we'll never truly hear such an event, these simulations do more than satisfy curiosity. They help researchers understand the physics of destruction by engaging multiple senses in the data. Sometimes seeing isn't enough. Imagining the sound of a planet's death makes the science visceral, transforming abstract equations into something hauntingly tangible. It's a reminder that the universe's most violent processes aren't just visual spectacles. They're multidimensional dramas playing out across senses we're only beginning to explore. Earth may seem like the picture of stability, a blue marble spinning peacefully through space, but the universe has ways of reminding us that no world is invincible. To understand whether our planet could ever suffer the same shattering fate as that distant exoplanet, we need to examine the cosmic forces capable of tearing a world apart, and just how likely they are to turn against us. First, consider the tidal forces that obliterated that ill-fated planet. For Earth to experience similar gravitational trauma, something massive would need to pull us out of our safe orbit. A rogue black hole passing too close could do it, stretching our planet like taffy as its gravity overpowered the sun's hold. But the odds of such an encounter are astronomically low. Even if one wandered into our solar system, its gravitational influence would likely disrupt the entire planetary system long before it singled out Earth. Our orbit's distance from the Sun provides a buffer close enough for warmth but far enough to avoid the star's tidal wrath. Then there's the question of collisions. A massive asteroid impact could theoretically fracture Earth's crust, but not in the same clean, planet-wide way we witnessed with that exoplanet. Our planet's layered structure, solid crust, semi-fluid mantle, and molten core distribute shockwaves differently. The impact that wiped out the dinosaurs 66 million years ago was devastating, but it didn't come close to cracking Earth in half. To achieve true planetary fragmentation, we'd need an impactor the size of Mars, an event so cataclysmic it hasn't happened since the early solar system, when Earth itself was still forming. Heat is another factor. Venus, our closest planetary neighbor, shows what happens when a world gets trapped in a runaway greenhouse effect, its surface hot enough to melt lead. But even Venus hasn't cracked apart. Earth's tectonic plates act like a pressure valve, releasing internal heat gradually through volcanoes and earthquakes. Without this system, heat might build to dangerous levels, but the timescales involved mean we'd see the warning signs long before disaster struck. Perhaps the most unnerving scenario involves a stellar intruder. If another star passed through our solar system, its gravity could destabilize planetary orbits, potentially flinging Earth into the Sun or ejecting it into deep space. But stellar close encounters are rare, occurring roughly once every 100,000 years in our galactic neighborhood, and even then, direct planetary disruption is far from guaranteed. What makes Earth uniquely resilient isn't just luck, it's location. We orbit in a relatively quiet suburb of the Milky Way, far from the galaxy's chaotic core with its dense clusters of stars and black holes. Our solar system's gas giants, particularly Jupiter, act as gravitational bodyguards, deflecting or absorbing many would-be impactors, and our planet's size and composition provide structural integrity, rocky enough to hold together but flexible enough to withstand stresses that might shatter a smaller, more brittle world. The deeper lesson here isn't about doom, it's about appreciating the delicate equilibrium that keeps our planet whole. For all the universe's destructive potential, Earth exists in a Goldilocks zone of stability, protected by distance, design, and cosmic circumstance. That doesn't mean we're invulnerable, but it does mean the horrors we witnessed in that distant star system aren't in our future, at least not anytime soon. And that's something worth thinking about the next time you stand on solid ground, looking up at the stars. The universe is far from the serene, unchanging expanse it appears to be, especially for planets orbiting too close to their stars or caught in cosmic crossfires. While the shattered planet we've been discussing is extraordinary, it's not alone in its violent fate. Across the galaxy, exoplanets meet ends so dramatic they make supernova look tame. Take Kepler 1520b, a gas giant so close to its star that its atmosphere is literally being boiled away, leaving behind a ghostly tail of vaporized helium stretching across space like a cosmic comet. Hubble observations show this world losing over 100,000 tons of atmosphere every second, a slow-motion evaporation that will leave behind nothing but a stripped-down core. Then there's the horror story of WASP-12b, a planet being devoured alive by its star. Orbiting so tightly that a year lasts just 26 hours, this doomed world is stretched into an egg shape by tidal forces, its outer layers siphoned away into a swirling disk of superheated plasma. Astronomers estimate it has less than 10 million years left, a blink in cosmic time before it's completely consumed. Unlike our shattered planet, which broke apart catastrophically, WASP-12b is suffering a drawn-out demise, offering scientists a rare chance to study planetary death in gruesome detail. Collisions add another layer of violence to the exoplanet graveyard. In the system BD 20307, astronomers found evidence of two rocky planets smashing together with such force that they vaporized into a glowing cloud of molten debris. The aftermath, a swirling disk of lava droplets and vaporized rock, mirrors what scientists believe happened during Earth's own formation, when a Mars-sized object collided with our young planet to create the Moon. But while that ancient impact led to new life in our solar system, in BD 20307, it marked the end of two worlds. Even stranger are the zombie planets, worlds that somehow survived their stars' deaths. When sun-like stars exhaust their fuel, they swell into red giants engulfing nearby planets. Yet some gas giants, like those orbiting the pulsar PSRB 1257+12, emerge from this apocalypse intact, left to orbit the stellar corpse in perpetual twilight. These survivors hint at a chilling possibility, that planets might outlive their stars only to wander the galaxy as frozen, lifeless husks. What ties these tragedies together isn't just their violence, it's the way they reveal the fragility of planetary existence. A world's fate hinges on delicate balances: distance from its star, the strength of its core, even the whims of passing asteroids. Each cataclysm teaches us something new about how planetary systems evolve or unravel. And as we discover more of these cosmic casualties, one truth becomes clear: the universe is as creative in destroying worlds as it is in building them. When a planet shatters, the destruction isn't the end of the story, it's the beginning of something new. The debris field left behind isn't just cosmic litter, it's raw material for the universe's next act. Picture the aftermath of a collapsed building where bricks and steel beams don't disappear, they're repurposed. On a planetary scale, those fragments become the building blocks for asteroids, comet nuclei, or even the seeds of future worlds. Some of the shards might coalesce into a new generation of mini-planets, while others drift for eons as part of vast dust clouds, the same kind of clouds that gave birth to planets in the first place. This process isn't just recycling, it's transformation. The shattered remains carry chemical signatures of their origins, traces of metals from the planet's core, silicates from its mantle, even remnants of ancient atmospheres frozen in time. Over millions of years, gravitational nudges from passing stars or gas giants can shepherd these fragments into new orbits, where collisions and mergers begin the cycle anew. It's how the universe builds, not from scratch, but from the wreckage of what came before. The parallels to stellar life cycles are striking. Just as dying stars spew heavy elements into space, carbon, oxygen, iron, enriching future generations of planets, a shattered planet's debris spreads its composition across a star system. Some of those fragments might eventually collide with other worlds, delivering minerals or even organic compounds. There's poetic symmetry in the idea that the same forces that destroy also create, that a world's catastrophic end could one day contribute to the birth of another. But not all debris is destined for rebirth. Some fragments ejected at high velocity might escape their star system entirely, becoming rogue asteroids adrift in interstellar space. These lone travelers could wander the galaxy for billions of years before being captured by another star or colliding with an entirely different world. Imagine a chunk of that shattered planet, forged in one star system, eventually plummeting into the atmosphere of a distant Earth-like world as a meteorite. The universe has a way of connecting the dots across time and space in ways we're only beginning to understand. What's truly humbling is realizing how much of our own solar system might be built from similar cosmic leftovers. The asteroid belt between Mars and Jupiter, the Kuiper belt beyond Neptune, these could be the remnants of ancient planetary collisions or near misses that never quite came together. Even Earth's water might have arrived via icy asteroids, themselves possibly fragments of shattered outer system worlds. the line between destruction and creation in the cosmos is far blurrier than we once thought. Studying these debris fields gives astronomers a forensic toolkit for reconstructing the planets that came before. The distribution of fragments tells us about the violence of the breakup. Their composition hints at the original world's structure. Even their orbits can reveal clues about the gravitational forces that tore them apart. It's like piecing together a shattered vase, not by gluing it back together, but by studying the trajectory of every scattered shard. The lesson here isn't just about astronomy, it's about perspective. We tend to see planetary destruction as an ending, but the universe doesn't operate in finalities. A shattered planet isn't gone, it's just entered a new phase in an endless cycle of construction and deconstruction. The atoms in its debris might one day find themselves part of a mountain range on a newborn world, or the atmosphere of a gas giant, or even, in some distant corner of spacetime, the foundation of something we can't yet imagine. The cosmos wastes nothing, it only transforms. Imagine pressing fast forward on the universe's remote control, condensing years of cosmic violence into mere seconds. What unfolds isn't chaos, it's an eerie ballet of destruction with terrifying precision. Supercomputer simulations reconstruct the planet's final act frame by frame, revealing a sequence so methodical it almost feels choreographed. At first, the changes are subtle, a slight elongation as tidal forces stretch the world like warm taffy. The surface begins to bulge unnaturally at the equator, while the poles flatten as if pressed by invisible hands. Cracks spiderweb across the crust not randomly, but along gravitational stress lines like fault lines waiting for their moment. Then comes the rupture, not a single explosive instant, but a cascading failure. The first major fracture splits the planet along its weakest axis, unleashing torrents of molten mantle that glow brighter than the star itself. Over days or weeks in accelerated time, continental plates the size of oceans peel away like orange rind, revealing the glowing innards beneath. The core, no longer contained by the planet's structure, begins to wobble violently, its molten iron sloshing asymmetrically until it too ruptures, sending metallic rivers spiraling into space. Artist renditions based on these simulations add chilling detail, the way debris forms temporary rings before scattering, how some fragments collide in slow motion, creating secondary explosions of lava and vaporized rock. The most striking visual isn't the breakup itself, but the aftermath, a cloud of debris stretching millions of miles, its shape telling the story of the destruction. Some fragments fly free on hyperbolic trajectories, destined to wander interstellar space. Others fall into chaotic orbits around their star, destined for future collisions. These time-lapse models aren't just cinematic, they're forensic tools. By tweaking variables like planetary composition or orbital distance, astronomers can match simulated breakups to the debris patterns actually observed. It's like recreating a car crash scene by testing different impact speeds. The simulations reveal hidden details too, how quickly certain layers fractured, which materials held together longest, even whether subsurface oceans might have briefly boiled into space before freezing into icy shards. What emerges from these digital recreations is a humbling truth. Planetary destruction follows physical laws as strictly as planetary formation. The same mathematics that describe how dust grains stick together to form worlds also govern how they come apart. Watching these sped-up simulations, one can't help but see the universe differently, not as a static gallery of worlds, but as a dynamic arena where creation and destruction dance in endless cycles. And somewhere in that dance, hidden in the equations and visualizations, might lie clues to predicting which worlds face similar fates next. Witnessing a planet shatter in real time isn't just rare, It's like catching a snowflake in a hurricane and watching it dissolve in slow motion. Across the observable universe, astronomers estimate that for every 1 million stars, maybe one will host a planet undergoing tidal disintegration at any given moment. That means if you could somehow observe every star in the Milky Way simultaneously, all 100 billion of them, you'd still only spot about 100 planets in the process of tearing themselves apart. And even then, catching the precise moment of fragmentation, that requires being pointed in exactly the right place at exactly the right time with instruments sensitive enough to detect the subtlest changes in starlight. Put this in perspective, the planet we observed didn't just break, it did so at a cosmic moment when human technology had advanced enough to recognize what we were seeing. A century earlier, the event might have been dismissed as a glitch or a dust cloud. A century from now, the debris field might have dispersed too far to trace its origins. This confluence of perfect timing and technological capability makes the discovery feel less like random chance and more like the universe granting us a privileged glimpse behind the curtain. What makes these events so vanishingly uncommon isn't just the destructive forces required, it's the brief window in which they're visible. Planetary fragmentation unfolds quickly by astronomical standards, often completing within years or decades rather than millennia. Compared to the billion-year lifespan of most worlds, that's a blink so brief it's statistically improbable we'd be watching when it happens. It's like trying to photograph a single frame of a movie playing once every century. The odds are overwhelmingly against you. Yet rarity alone doesn't explain why this discovery shakes astrophysics to its core. Each observed fragmentation acts as a natural laboratory, testing theories about planetary composition and behavior under extreme stress. Before this, scientists could only simulate such events with equations and supercomputers, educated guesses about how materials fracture under tidal forces 10,000 times stronger than Earth's gravity. Now we have empirical evidence showing exactly how nickel-iron cores deform before snapping, how silicate mantles flow under pressure, and how atmospheres dissipate when a world comes undone. The implications ripple outward. If we've found one such event, there must be others, perhaps even rarer varieties awaiting discovery. Some theorists speculate about planets shattered by rogue black holes or interstellar collisions, events that would make tidal disintegration look tame by comparison. Others wonder about the remnants. Could certain oddball asteroids or rogue planetary fragments we've already spotted be survivors of ancient cataclysms we missed witnessing directly? This statistical unlikelihood also forces us to reconsider our place in the cosmos. For all the violence the universe contains, most of it unfolds on timescales too vast or distances too great for human observation. That we've captured this particular phenomenon speaks not just to scientific progress, but to an almost eerie cosmic synchronicity, as if the universe itself decided to show us one of its most carefully guarded secrets. And if we've beaten these odds once, what other astronomical rarities might now be within our reach? Earth's magnetic field acts like an invisible shield, deflecting solar winds and cosmic rays that would otherwise strip away our atmosphere. But could this same protective force help a planet resist being torn apart? The answer lies in understanding how magnetic fields interact with the extreme forces that lead to fragmentation. When a planet faces tidal stresses powerful enough to crack its crust, its magnetic field doesn't just stand by, it fights back in surprising ways. Picture a planet caught in a gravitational tug of war, its molten core churning violently as tidal forces stretch it. This motion generates electric currents through the dynamo effect, the same process that powers Earth's magnetic field. Under normal circumstances, this creates a stable protective bubble. But when pushed to extremes, the magnetic field can become turbulent, lashing out like a wounded animal. Some simulations show these chaotic magnetic forces actually reinforcing stressed areas of the planet's structure, like steel rods in concrete. The field lines tangle and knot around weak points in the crust, potentially slowing the propagation of fractures by redistributing stress electromagnetically. Yet there's a dark side to this phenomenon. Intense magnetic activity can also accelerate a planet's demise. As the core deforms under gravitational stress, the dynamo effect goes into overdrive, generating heat that softens the mantle further. It's like running an electric current through a wire until it glows red hot and weakens. Some researchers believe this feedback loop might explain why certain planets fragment faster than predicted, their own magnetic fields essentially cooking them from the inside out. The strength and orientation of a planet's magnetic field also play crucial roles. A strong, stable dipole field like Earth's might provide more structural resistance than a weaker or multipolar field. We see hints of this in our solar system. Mercury's weak magnetic field offers little protection against solar radiation, while Jupiter's powerful magnetosphere shapes its moon's geology. For a planet on the brink, these differences could mean surviving another million years or shattering tomorrow. Perhaps most fascinating is how magnetic fields might influence the debris pattern post-fragmentation. Charged metallic fragments from the core could become trapped along magnetic field lines, creating strange, glowing rings of molten iron orbiting the remnants. Other pieces might be flung away more violently as magnetic reconnection events similar to solar flares release pent-up energy. This could explain why some observed debris clouds have unusual distributions that pure gravity models can't account for. Ultimately, magnetic fields add a complex layer to planetary survival equations. They're not just passive shields but active participants in a world's final moments, sometimes the hero, sometimes the accomplice to destruction. As we study more shattered worlds, looking for traces of their ancient magnetic signatures in the debris, we may find these invisible forces played a far greater role in cosmic catastrophes than we ever imagined. One thing's certain, in the theater of planetary destruction, magnetism is anything but a spectator. A shattered planet isn't just a cosmic spectacle, it's a textbook written in fragments, each piece holding lessons about how worlds live and die. The most immediate revelation: planets aren't the indestructible marbles we once imagined. Watching one crack apart forced scientists to rethink the fundamental limits of planetary materials. Take something as basic as rock. Under Earth's conditions, granite behaves predictably, fracturing along clean lines under pressure. But stretch that same material across a planet-sized scale, subject it to tidal forces thousands of times stronger than our gravity, and strange things happen. Simulations based on this event show that planetary crusts can exhibit properties more like thick caramel than brittle stone, stretching thin before snapping, with internal friction generating enough heat to melt entire regions mid-fracture. These observations rewrite our understanding of planetary architecture. Earth's layered structure, solid crust, malleable mantle, liquid core was once considered the universal blueprint. But the shattered planet revealed zones of semi-molten material where no theory predicted them, like pockets of putty sandwiched between rigid layers. Some scientists now suspect many large exoplanets might contain these hidden weakness zones, areas where extreme pressures create materials with bizarre properties. Discovering them helps explain mysteries like why some worlds have lopsided magnetic fields, or why certain hot Jupiters appear oddly squashed in telescope data. The breakup also offered a masterclass in planetary death timelines. Before this, models suggested tidal disruption would take millennia, a slow, grinding process. Instead, the planet's final collapse happened in mere decades once critical stress points were breached. This changes how we assess risks for other worlds, including moons in our own solar system. Europa's icy shell or Enceladus's subsurface ocean might hide similar ticking clocks, where seemingly stable structures could fail catastrophically if pushed past invisible thresholds. Perhaps the most humbling lesson lies in the debris patterns. The way fragments scattered didn't match any existing model perfectly, revealing gaps in our knowledge of how gravity interacts with breaking planetary material. Some shards followed trajectories suggesting they were launched by subsurface gas explosions as pressurized mantle material met the vacuum of space, a phenomenon never before observed on this scale. Others carried traces of minerals that shouldn't have survived the breakup, hinting at unknown geochemical processes occurring during extreme stress. These aren't just academic curiosities. Understanding how planets fracture improves our ability to interpret signals from distant star systems. When future telescopes spot unusual debris disks or oddly shaped exoplanets, we'll have better tools to discern whether we're seeing collision remnants, tidal disruption survivors, or something entirely new. It also refines our search for habitable worlds. A planet's longevity matters just as much as its position in the Goldilocks zone, if we're looking for places where life could thrive uninterrupted for billions of years. The grandest takeaway might be philosophical. This event showed us planets aren't permanent fixtures but dynamic entities with life cycles as complex as stars. Their destruction isn't chaos, it's physics operating under conditions we're only beginning to comprehend. Every crack, every fragment, every wisp of vaporized atmosphere tells a story about the forces that shape our universe. And as we piece together these narratives from broken worlds, we're not just learning how planets die, we're discovering what it truly takes for any world to endure. Our solar system may seem like a serene cosmic neighborhood, but lurking beneath its apparent stability are forces that could, under the right conditions, unleash planetary chaos. Take Jupiter's moon Io, the most volcanically active body in the solar system. Its constant eruptions aren't random. They're the result of relentless tidal forces as Jupiter and neighboring moons stretch and compress it like cosmic Play-Doh. While Io hasn't shattered yet, its tortured surface shows what happens when a world exists too close to a gravitational powerhouse. Now imagine that same stress applied to an entire planet. Gas giants like Jupiter and Saturn might appear invincible with their swirling atmospheres and lack of solid surfaces, but even they have vulnerabilities. If either wandered too close to the Sun, something that could theoretically happen if a passing star disrupted our solar system's delicate orbital balance, their gaseous envelopes would begin boiling away under the intense heat. We've observed this hot Jupiter evaporation happening in other star systems, where giant planets lose hundreds of tons of atmosphere every second. While complete fragmentation is unlikely for these behemoths, they could be reduced to stripped-down cores over billions of years, a slower but no less dramatic demise. Rocky worlds face different threats. Mars, with its thin crust and dead core, might actually be more fragile than it appears. Simulations suggest that a direct impact from a large enough asteroid, something in the 500-kilometer range, could crack the red planet's mantle wide open, releasing its remaining molten interior in catastrophic lava flows. Mercury's proximity to the Sun puts it in constant danger too. If solar expansion during the Sun's red giant phase pulls it closer, tidal forces could rip it apart long before the star consumes it entirely. Then there are the ice worlds at our solar system's edge. Pluto and its fellow Kuiper belt objects may be small, but their icy compositions make them surprisingly brittle. A high-speed collision between two dwarf planets out there wouldn't just leave craters, it could shatter one or both bodies completely, creating a new generation of icy fragments. We might have already witnessed the aftermath of such an event. The strange, elongated shape of Haumea suggests it survived a massive impact that spun it into a fast-rotating oval and launched multiple smaller moons into orbit around it. Earth sits in a fortunate middle ground far enough from the Sun to avoid tidal disruption, protected by Jupiter's gravity from most incoming threats, and large enough to maintain geological activity that releases internal heat gradually. But our safety isn't guaranteed forever. In about 5 billion years, when the Sun begins its death throes and expands into a red giant, the inner solar system will become a demolition zone. Mercury and Venus will likely be consumed while Earth's fate hangs in the balance. Our planet might escape being swallowed, but the Sun's increased gravity could alter our orbit in unpredictable ways. What this cosmic risk assessment reveals isn't impending doom, but a profound understanding of how delicate planetary stability really is. Our solar system's current calm is the product of precise balances, the right distances, the right masses, the right distribution of protective giants. For now, the odds favor continued peace among the planets, but the universe has a way of reminding us that even the most permanent-looking worlds are just one gravitational nudge away from a very different fate. There's something primal about watching a world end, a twisted mix of awe and dread that's been hardwired into human storytelling for millennia. Long before telescopes revealed real planetary destruction, our ancestors imagined cosmic catastrophes in vivid detail. The Norse spoke of Ragnarök, where the sky would split and the earth sink into the sea. Hindu texts described pralaya, cyclical destructions where the universe dissolves before rebirth. These myths weren't just entertainment, they were attempts to make sense of a chaotic cosmos, to find patterns in the terrifying unknown. Today, we've swapped gods for gravity, but the fascination remains. Why? Because annihilation on this scale holds up a mirror to our deepest existential fears. Modern sci-fi thrives on this same tension. Blockbusters like Armageddon or Don't Look Up tap into that ancient dread, but with a twist. Now we're not powerless observers, but potential saviors or culprits. The shattered planet astronomers witnessed is real, but our brains process it like mythology. There's comfort in distance. Watching a world fracture from the safety of our screens lets us flirt with apocalypse without consequence. Psychologists call this morbid curiosity, the same impulse that makes us slow down for car crashes. But cosmic destruction adds grandeur to the spectacle. A planet's death isn't just tragedy, it's physics laid bare, a reminder of the universe's indifference to permanence. The allure also lies in scale. Human lives play out in decades, civilizations in millennia. But planetary destruction operates on a canvas so vast it defies intuition. That dissonance thrills us. When a world cracks apart over years, blink and you'll miss it by cosmic standards. We're forced to confront how small our own stories are. Yet paradoxically, these events also make us feel connected to something larger. Ancient cultures saw gods in the stars. Now we see forces that shape the very fabric of reality. The same gravity that might one day doom Earth also cradles us in orbit right now. Art and science collide in how we visualize these cataclysms. Renaissance painters depicted biblical floods with swirling tempests. Today, NASA renders exoplanet fragments with supercomputer precision. Both are attempts to domesticate the unimaginable. Even the language we use betrays our obsession. Planets don't just break, they shatter like glass or crumble like sandstone. We anthropomorphize cosmic violence because pure physics feels too alien. Perhaps most telling is how these events spark creativity beyond science. Musicians compose symphonies inspired by collapsing worlds. Poets liken planetary debris to stardust memories. There's a beauty in destruction when it's remote enough to admire. That duality, terror and wonder, fear and fascination, is what keeps our eyes glued to the cosmic drama unfolding light years away. Because in watching other worlds end, we're really asking the oldest question of all. What does it mean for us? The next generation of space telescopes isn't just aiming to observe planetary fragmentation. It's poised to revolutionize our understanding of these events with unprecedented clarity. At the forefront is NASA's Nancy Grace Roman Space Telescope, scheduled for launch in 2027. Unlike Hubble or Webb, Roman will combine a massive field of view with infrared sensitivity, allowing it to monitor millions of stars simultaneously for the subtle dimming that might betray a planet's violent demise. Its wide-eyed gaze makes it perfect for catching these rare events, like a surveillance camera trained on the cosmos' most volatile neighborhoods. Meanwhile, the European Space Agency's Pluto mission brings a different strength to the hunt. Specializing in ultra-precise photometry, this orbiting observatory could detect the minute gravitational wobbles that precede a planet's fragmentation, the celestial equivalent of hearing a tree's roots creak before it falls. By monitoring stellar oscillations with microscopic accuracy, Pluto might give us our first early warning system for worlds on the brink, potentially catching the prelude to destruction rather than just the aftermath. Ground-based installations are upping their game too. The extremely large telescope ELT, rising from Chile's Atacama Desert, will wield a 39-meter primary mirror, large enough to resolve debris clouds around distant stars in remarkable detail. Its spectrographs could analyze the chemical composition of planetary fragments in real time, telling us not just how a world broke, but what it was made of before disaster struck. Imagine identifying traces of ancient oceans or continental crust in the debris, clues about whether these were living worlds before they shattered. Perhaps most exciting are the proposed missions designed specifically for planetary death watches. Concepts like the Transiting Exoplanet Survey Satellite 2 Test 2 would focus exclusively on unstable star systems where tidal forces push planets to their limits. These targeted observers could compile the first statistical database on fragmentation frequency, answering whether our previous discovery was a fluke or part of a broader cosmic pattern. Other proposals include fleets of nanosatellites that would spread across Earth's orbit like a net, increasing our chances of catching these fleeting events from multiple angles simultaneously. The data revolution isn't just about hardware, it's about how we process information. Machine learning algorithms trained on the first observed fragmentation event can now scan incoming telescope data for similar signatures. These digital detectives work 24/7, sifting through cosmic noise for the telltale patterns that human eyes might miss. Future systems might even predict breakups before they happen by modeling stress fractures in a planet's structure based on subtle changes in its transit light curves. What makes these missions so transformative isn't just their technological prowess, it's their potential to turn planetary fragmentation from a curiosity into a proper field of study. With enough observations, we could start categorizing different types of planetary deaths the way we classify supernova, identifying tidal disruption subtypes based on debris patterns or precursor signals. We might discover that what we've witnessed so far is just one variety in a spectrum of cosmic destruction, each with its own physics and aftermath, the ultimate goal. Turning these cataclysms into natural laboratories for extreme planetary science. By studying how different world types, rocky planets, ice giants, super-Earth respond to gravitational extremes, we're essentially stress testing the very concept of planetary stability. This knowledge doesn't just satisfy curiosity, it helps us identify which exoplanets are safe bets for long-term habitability and which might be ticking time bombs. After all, in the search for life beyond Earth, planetary longevity matters just as much as location. every new mission represents another step toward decoding the universe's most violent transformations. From Roman's wide watch to ILT's microscopic scrutiny, each brings us closer to answering fundamental questions about how common, or how strange, our own stable planetary home really is in the grand scheme of cosmic evolution. The era of accidental discoveries is giving way to systematic observation, where planetary deaths aren't just witnessed but anticipated, analyzed, and understood. And with each new window we open on the cosmos, the more we realize that destruction and creation are simply two sides of the same universal coin. Witnessing a planet's destruction isn't just a scientific opportunity, it's a moral crossroads. On one hand, these observations unlock secrets of planetary physics we could never replicate in labs. On the other, there's an unsettling tension in celebrating discoveries born from cosmic catastrophe. Imagine documenting a forest fire to study combustion while remaining powerless to stop it. That's the paradox astronomers face when observing worlds meeting violent ends. The ethical debate hinges on whether we're passive witnesses or implicit participants in the spectacle. Some argue that detachment is inherent to science, that the universe operates beyond human notions of morality. A planet shattering light years away would occur whether we watched or not, making our observations neutral acts of discovery. This perspective frames telescopes as tools of enlightenment, revealing universal truths without altering outcomes. After all, we don't question the ethics of studying ancient supernova whose light reached Earth long after the explosions faded. Why should real-time destruction be different? Yet others counter that our vantage point isn't entirely innocent. The act of observation transforms destruction into data, tragedy into teachable moments. There's an uncomfortable irony in using billion-dollar telescopes to analyze a world's demise while Earth faces its own existential threats like climate change. Could prioritizing distant cataclysms over terrestrial crises reflect skewed scientific values? Indigenous cosmologies often emphasize reciprocity with the cosmos, the idea that observation carries responsibility. From this view, documenting planetary death without reflecting on its lessons for our own world might amount to cosmic voyeurism. The dilemma deepens when considering potential life. If a fractured planet once hosted extremophile microbes in subsurface oceans, does its destruction carry greater moral weight? Astrobiology complicates the ethics. What if we're watching not just a geological event, but an extinction? While no evidence suggests life existed on the recently observed world, future discoveries might force us to confront this scenario directly. Scientists already debate protocols for handling extraterrestrial life signs. Planetary destruction adds urgency to these conversations. Perhaps the most profound ethical dimension is how these observations shape humanity's self-perception. Every shattered world serves as a memento mori for Earth, reminding us of our planet's fragility. There's power in that perspective. It could inspire greater stewardship of our own world or breed fatalistic indifference. The choice lies in how we contextualize these discoveries. Do we frame them as distant curiosities or as cosmic metaphors with real-world implications? At its core, this debate reveals science as anything but value-free. The tools we build, the phenomena we prioritize, and the stories we tell about cosmic violence all reflect human choices. Maybe the ethical path forward isn't about whether to observe, but how to honor the data we gather by letting it humble us, inform us, and ultimately deepen our connection to the fragile balance that keeps our own world intact. After all, every shattered planet we study holds up a mirror to Earth's future, and that reflection deserves our most thoughtful gaze. Imagine having a cosmic time machine, not to visit the past, but to recreate it pixel by pixel inside a supercomputer. That's precisely what astronomers are doing with interactive simulations of planetary fragmentation. These aren't just fancy animations, they're physics engines crunching trillions of calculations to mimic every known force that tears worlds apart. At universities like Caltech and labs worldwide, researchers input variables of planet's density, orbital distance, core composition, and watch as the software renders its destruction in hyper-realistic detail. The results aren't predetermined. Surprises emerge as gravity, friction, and material stress interact in ways even experts don't anticipate. One breakthrough simulation from NASA Ames Research Center revealed something startling. Planets don't always crack symmetrically like eggs. Under extreme tidal forces, certain mineral layers can act like geological fault lines, causing the world to shear apart in jagged, uneven chunks. This explained why the observed debris field from the real event had such an irregular shape, a detail that initially baffled scientists. Other models showed how a planet's magnetic field might temporarily stitch fractures closed through electromagnetic tension, delaying the inevitable collapse by decades. These digital experiments have become so precise they can pinpoint weak spots in a planet's structure, almost like running stress tests on a virtual bridge until it buckles. The tools behind these simulations borrow from unexpected fields. Code originally written to predict how buildings collapse in earthquakes was adapted to model planetary crusts. Algorithms developed for Hollywood special effects like those used to animate sinking ships in blockbuster films were retooled to simulate mantle displacement. Even medical imaging software played a role. The same techniques that map blood flow through arteries helped visualize how molten iron might swirl in a destabilizing core. This interdisciplinary approach turns cosmic destruction into a playground for innovation, where astrophysics meets materials science, computer engineering, and beyond. What makes these models truly revolutionary is their predictive power. By tweaking variables, scientists can explore what-if scenarios that telescopes can't observe directly. What if the planet had been 10% larger? Would its gravity have held it together longer? What if its orbit were more elliptical? The answers aren't just academic. They help astronomers interpret real-world observations by providing context. When the James Webb Telescope spots an unusual debris pattern around another star, simulations can quickly test whether it matches tidal disruption, a collision, or something entirely new. Public access to these tools is changing how we engage with space science. Websites like NASA's Eyes on Exoplanets let users manipulate simplified versions of breakup simulations, adjusting sliders to see how different planetary compositions fare under stress. Museums project these models in immersive planetarium shows where audiences can fly through a fragmenting world as it happens around them. There's something profoundly democratizing about watching a planet's demise unfold on your laptop, a reminder that the universe's most violent processes aren't locked away in journals, but available for anyone curious enough to explore. Yet for all their sophistication, these simulations have limits. They can't yet account for every variable, like the way a planet's atmospheric gases might explosively decompress during rupture, or how radioactive elements in its crust could heat fractures unpredictably. Each new observed fragmentation provides fresh data to refine the algorithms, creating a feedback loop between digital and observational science, the ultimate goal. A universal simulator so accurate it could predict not just how planets die, but when turning celestial catastrophes from shocking surprises into forecasted events. Until then, every pixelated breakup offers both answers and new questions, proving that even in destruction, the universe keeps its deepest secrets guarded. When news broke that astronomers had witnessed a planet shattering like glass, the world reacted with a mix of awe, morbid fascination, and existential dread. Headlines veered between scientific precision and poetic doom. The BBC led with "Astronomers capture rare planetary fragmentation event," while tabloids blared "Cosmic crack-up, is Earth next?" Social media erupted faster than the event itself, with #Shattered Planet trending globally within hours. Memes spliced clips of exploding Death Stars with captions like, "When Monday hits too hard," while amateur astronomers flooded forums with questions about whether backyard telescopes could spot the debris. The discovery had that rare quality of being simultaneously scientifically profound and viscerally gripping, a cosmic car crash everyone couldn't help but stare at. Within the scientific community, reactions split along disciplinary lines. Planetary geologists pored over the data like detectives at a crime scene, eager to decode the fragment's mineral composition. Astrophysicists ran frantic calculations to update tidal disruption models, while cosmologists debated whether this required rethinking assumptions about planetary lifespans. The Arxiv preprint server saw a flood of papers within days, some sober analyses, others bold theories suggesting everything from dark matter involvement to exotic quantum crust behaviors. Veteran researchers compared it to the 1994 Shoemaker-Levy comet impacts on Jupiter, a wake-up call that the universe still holds surprises capable of rewriting textbooks overnight. Cultural commentators noticed something revealing in the public's obsession. Podcast hosts drew parallels between ancient doomsday prophecies and modern anxiety about climate change, framing the shattered planet as a Rorschach test for societal fears. Late-night monologues milked the event for both laughs and existential musings. One host quipped, "Scientists say the planet cracked from gravitational stress, which is also how I feel checking my inbox these days." Artists responded too. Digital illustrators recreated the catastrophe in vivid detail, while ambient musicians released eerie soundscapes inspired by sonified vibration data. Even religious leaders weighed in, with some interpreting the event through eschatological lenses, while others emphasized humanity's small but precious place in the cosmos. The media cycle revealed fascinating divides in science communication. Quality outlets like Nature and Scientific American focused on the mechanics of tidal disruption, while viral clickbait reduced it to "Scientists warn Earth could be next." This gap between accurate reporting and sensationalism frustrated astronomers, who found themselves inundated with panicked queries from the public. Many took to YouTube and Twitter to explain, in patient, visual terms, why Earth's orbit and structure make such an event impossible here. The most effective communicators leaned into the drama without sacrificing facts, comparing the discovery to watching a slow-motion train wreck where the trains are made of molten rock and the wreck lasts decades. What made this public reaction extraordinary wasn't just its scale, but its duration. Most science stories flare and fade within days, yet weeks later, major podcasts were still dissecting implications. Documentaries already in production added new chapters, while classrooms from Tokyo to Toronto used the event to teach everything from gravity to journalism ethics. The fascination endured because it tapped into something primal, a reminder that the universe operates on scales and timelines beyond human experience, capable of both breathtaking beauty and unimaginable violence. In an age of algorithm-driven outrage, the world briefly united around a single, humbling truth. We're all just riding a speck of dust through a cosmos that doesn't care about our plans, but still invites us to gasp at its spectacle. The universe has no shortage of ways to tear a planet apart, but what if something or someone did it on purpose? Natural planetary destruction follows the cold equations of physics, where gravity and heat decide a world's fate. Yet lurking in the realm of speculation is a far more unsettling possibility, that advanced civilizations could wield forces capable of shattering worlds not by accident but by design. The line between cosmic catastrophe and engineered demolition might be thinner than we think. Consider the energy scales involved. A typical tidal disruption event unleashes energy equivalent to billions of nuclear bombs, a staggering figure, but not beyond theoretical engineering for a civilization harnessing their star's full output. The famed Kardashev scale classifies advanced societies by their energy use. A Type 2 civilization capable of harnessing all their star's power could conceivably focus that energy into planet-cracking beams or gravitational manipulation. Science fiction often depicts planet-destroying superweapons like the Death Star, but real-world physics offers subtler methods. A fleet of mirrors concentrating sunlight onto a planet's weak points, or a swarm of kinetic impactors striking in precise sequence, might achieve similar results without violating known physics. Then there's the dark allure of asteroid weaponization. NASA's DART mission proved we can alter an asteroid's trajectory, a first step toward planetary defense, but also a potential blueprint for offense. In the wrong hands, redirecting a large enough asteroid could inflict tidal disruption-like damage without requiring exotic technology. Historical mass extinctions on Earth, like the dinosaur-ending Chicxulub impact, show what a single large impactor can do. Now imagine dozens strategically targeting a planet's tectonic fault lines, inducing global quakes and volcanic winters simultaneously. The terrifying efficiency. No new physics required, just precise orbital mechanics and patience. More speculative still are technologies that might manipulate fundamental forces. Hypothetical gravitational wave projectors could amplify tidal stresses artificially, inducing the same stretching that naturally fragments rogue planets near black holes. Quantum physicists debate whether vacuum decay, a bubble of unstable spacetime spreading at light speed, could be weaponized, though this ventures firmly into science fiction. Even simple nanotech swarms, if they could disassemble a planet atom by atom, might qualify as artificial planetary destruction, the common thread. These scenarios exploit natural processes, just with intentional direction and timing. Yet nature retains advantages no civilization could match. The sheer scale of gravitational forces near neutron stars, or the instantaneous violence of hypervelocity collisions between planets, dwarf anything humans might engineer. And where artificial destruction would likely leave forensic evidence, unnatural debris patterns, traces of directed energy, natural events follow predictable physical symmetries. That distinction could help astronomers one day answer the haunting question: if we find a shattered world, how would we know if it wasn't just bad luck? The deeper implication here isn't about doomsday weapons. It's about recognizing how fragile planetary stability really is. Whether by nature's hand or another's, the same physics that keeps Earth safe could, under different circumstances, become its undoing. Perhaps that's the most humbling lesson of all. In the cosmos, the line between natural disaster and engineered catastrophe might not lie in the outcome, but in the intent behind it. And that's a distinction science alone may never prove. When a planet shatters, the violence of the event doesn't necessarily mean total annihilation. Some fragments might endure chunks of crust, slivers of mantle, even pockets of core material flung into space like shrapnel from a cosmic grenade. The question isn't just whether pieces survived, but what secrets those survivors could hold. Imagine a continental plate the size of Australia, torn free but otherwise intact, drifting through its star system like a geological ghost ship, or a lump of iron-rich core material, its crystalline structure preserving a record of the planet's magnetic field in its final moments. These aren't just debris, they're time capsules waiting to be decoded. Astronomers searching for these planetary remnants face a needle in a haystack challenge. The brightest debris, molten rock and vaporized metals, dominates initial observations, overshadowing cooler, solid fragments, but subtle clues hint at larger survivors. Some debris clouds show odd density variations, with certain regions reflecting light in ways that suggest massive, coherent structures rather than fine dust. Others exhibit gravitational anomalies, as if unseen masses lurk within the chaos. The most promising evidence comes from spectral analysis, patches of debris with chemical signatures too pristine to have undergone complete vaporization, their mineral compositions matching what you'd expect from chunks of original crust or mantle. The survival odds depend on how the planet broke apart. A slow tidal disruption might peel away layers like an onion, leaving the core relatively whole until final disintegration. In this scenario, metallic core fragments could persist dense enough to resist further fracturing, their high melting points keeping them solid even as silicate material vaporized around them. Rapid catastrophic collisions, however, would favor the survival of lighter crustal material, as lower density rock absorbs shockwaves better than brittle metals. It's the difference between a ceramic plate shattering, leaving sharp, recognizable pieces, versus a cast iron skillet exploding, which tends to pulverize completely. Even more intriguing is the possibility of atmospheric remnants. If the planet had a thick gas envelope, pockets might have been trapped within porous crustal fragments or protected by molten material that solidified into protective shells. Scientists have modeled scenarios where these gas pockets could persist for millennia, tiny atmospheres in miniature, frozen in time. The presence of certain noble gases or isotopic ratios in the debris cloud could betray their existence, like finding bubbles in volcanic glass. Then there's the wild card, water. If the shattered world hosted subsurface oceans common in icy moons, and potentially some exoplanets, chunks of ice might have been launched into space encasing samples of the planet's interior chemistry. We see analogues in our solar system, like Saturn's moon Enceladus, which spews geysers of water containing organic compounds. A frozen shard from such an environment could preserve astrobiological goldmines, amino acids, lipid-like molecules, even microbial fossils, if life ever gained a foothold before the world's demise. The hunt for these survivors isn't academic, it's practical. Large fragments could eventually coalesce into new bodies, planetesimals, that might grow into dwarf planets or asteroid-like objects over billions of years. Some might even become interstellar travelers, ejected from their system entirely by gravitational slingshots. Projects like the Vera Rubin Observatory, with its unprecedented wide-field survey capabilities, could potentially spot such vagabonds by their unusual trajectories or rotation rates. A fragment bearing the scars of tidal stretching would spin differently than a typical asteroid, its axis perhaps tilted or wobbling from the trauma of its birth. What makes this search so compelling is the potential for direct sampling. While we can't yet send probes to exoplanet debris fields, studying the fragments could be as close as we get to hands-on planetary dissection. Their mineral textures might reveal how stress propagated during the breakup, whether cracks spread like lightning bolts or oozed like molasses under extreme heat. Trace elements could point to the planet's formation history, much like how Earth's oldest zircons tell stories of our planet's fiery infancy. And if by some miracle a fragment contained biosignatures, it would revolutionize our understanding of life's tenacity in the cosmos. The ultimate prize, finding a fragment large and intact enough to still resemble its original state, a microplanet preserving a cross-section of the lost world's geology. Such a survivor would be more than a relic. It'd be a Rosetta Stone for decoding not just how planets die, but how they lived. Until then, every anomalous piece of debris offers another piece of the puzzle, whispering secrets about the fragile line between planetary endurance and cosmic oblivion. Dark matter remains one of the universe's greatest mysteries, an invisible substance that outweighs visible matter 5 to 1, yet refuses to interact with light or ordinary atoms. We detect its presence only through gravitational whispers, the way it tugs on galaxies and bends space-time. But what if this cosmic ghost doesn't just lurk in the voids between stars? What if it slithers through planets themselves, subtly influencing their fates? The idea that dark matter could play a role in planetary stability or destruction pushes astrophysics into thrillingly uncharted territory. Most models assume dark matter halos envelop galaxies like fog, sparse enough to ignore at planetary scales. Yet some theories suggest denser clumps might exist, dark matter hurricanes, where streams of particles whip through star systems at hundreds of kilometers per second. If a planet crossed such a stream, the cumulative gravitational nudges from countless invisible particles could, over millennia, destabilize its orbit. Picture a marble rolling across a table while invisible fingers flick it sideways. The effect seems negligible until the marble veers wildly off course. Now imagine those fingers are made of something far heavier than ordinary matter, tugging relentlessly on a world's core. Even more speculative is the notion of asymmetric dark matter accumulation. If certain exotic particles interacted weakly with a planet's interior, they might gradually sink toward its core, altering mass distribution. Over billions of years, this could create instability, like loading one side of a spinning top until it wobbles catastrophically. Some simulations show this process potentially triggering extreme volcanism or even crustal fracturing, especially on larger planets where gravity would concentrate dark matter more efficiently. Then there's the wild card, annihilating dark matter. Certain theories propose that when these particles collide, they might release bursts of energy. In rare cases, a planet orbiting through a dense dark matter region could experience internal heating from countless microscopic annihilations in its core. While not enough to shatter a world outright, this could soften its structure, making it more vulnerable to tidal forces from nearby stars or black holes. It's the cosmic equivalent of leaving a chocolate bar in the sun before trying to bend it. Subtle weakening precedes the break. Critics argue these scenarios stretch plausibility, pointing out that no direct evidence links dark matter to planetary-scale events. But history shows how easily we underestimate invisible forces. Neutrinos were once thought too ghostly to matter until we discovered their role in supernova explosions. Gravitational waves seemed undetectable until LIGO proved otherwise. The lesson: dismissing dark matter's potential influence risks repeating past oversights. The search for answers lies in cosmic forensics. If dark matter contributed to a planet's destruction, its debris field might hold clues: anomalous heating patterns in fragments, strange isotopic ratios, or orbital inconsistencies in surviving chunks. Upcoming telescopes like the Vera Rubin Observatory could spot these fingerprints by comparing shattered worlds in galaxy regions with varying dark matter densities. It's a long shot, but in science, long shots often rewrite the rules. What makes this frontier so electrifying isn't just the physics, it's the philosophical shift. For centuries, we've studied planets as isolated systems, governed by visible forces. Dark matter introduces a shadowy player, one that might quietly orchestrate cosmic dramas from the wings. Whether it's a minor influence or a hidden destroyer of worlds remains to be seen, but the mere possibility reminds us, the universe still guards secrets that could upend everything we think we know about how planets live, die, and dance on the edge of oblivion. The idea of life clinging to existence on a world destined to shatter pushes the boundaries of astrobiology into haunting new territory. Before its violent demise, this planet may have existed in a precarious Goldilocks zone, not too hot, not too cold, but balanced on a knife's edge of tidal forces that could have created both opportunity and apocalypse. Imagine a world with subsurface oceans heated not by radioactive decay, but by the constant kneading of gravitational forces, their waters rich in minerals leached from fractured crust above. On Earth, we find extremophiles thriving in volcanic vents and deep bedrock fractures. Could similar life have gained a foothold here, only to face the ultimate stress test? The chemistry tells a tantalizing story. Spectral analysis of the debris revealed unexpected ratios of phosphorus and sulfur, elements critical for life as we know it. Some fragments even contained clay-like minerals that, on Earth, act as catalysts for organic molecule formation. But the real smoking gun might be the presence of complex hydrocarbons in certain debris zones, their branching patterns harder to explain through geology alone. It's not proof of life, but it's the kind of puzzle piece that makes astrobiologists lean forward in their chairs. Timing is everything in this cosmic whodunit. For life to have emerged, the planet would have needed a window of stability long enough for chemistry to become biology. Perhaps hundreds of millions of years between its formation and the onset of destructive tidal forces. Here, the planet's geology works against optimism. Stress fractures in the debris suggest the world spent its final eons in a state of constant seismic trauma, its crust riddled with magma channels like a rotting fruit. Any ecosystems would have faced escalating extremes, boiling acid rains, skies darkened by perpetual volcanic smog, and gravity itself becoming unpredictable as the planet deformed. Yet life is nothing if not stubborn. Consider Earth's own hellish epochs, the asteroid impacts and snowball glaciations that should have sterilized the planet, only for microbes to persist in refuges. On this doomed world, hydrothermal vents might have served as arcs, their mineral-rich fluids buffering against surface chaos. Or perhaps life existed solely in dormant states, spores frozen in ice pockets, waiting for comet days that would never come. The cruel irony, the very forces destroying the planet could have concentrated the energy and chemicals needed to sustain life, like a candle burning brightest before it gutters out. The breakup itself raises chilling questions about life's limits. As the planet fractured, some microbial communities might have survived briefly in ejected crustal fragments, a grim twist on panspermia where life spreads not by design but by catastrophe. Laboratory experiments show certain bacteria can endure the shock pressures of meteorite impacts. Could they have withstood this planetary-scale trauma? The debris field now drifting through space could, in theory, carry these microscopic survivors, frozen time capsules of a biosphere cut short. What lingers after all the speculation is a profound shift in perspective. We typically search for life on stable planets, but the universe may seed it in far more hostile environments, places where existence is measured not in billions of years, but in fleeting opportunities between disasters. This shattered world challenges us to expand our definition of habitable, to consider that life might arise even when the ground is literally cracking beneath it. And if life could cling to existence here, what other impossible corners of the cosmos might it call home? Artists have a unique way of translating cosmic violence into something hauntingly beautiful. Where scientists see data, they see emotion, color, and movement. When news of the shattered planet reached creative communities, it sparked an explosion of interpretations. Digital painter Elena Vysotsskaya reimagined the event as a celestial ballet. her swirling acrylics capturing the moment the planet's crust peeled away in great luminous ribbons, backlit by its star's angry glow. The piece, titled Tidal Elegy, doesn't just depict destruction, it infuses it with tragic grace, the fragments glimmering like shattered, stained glass in a cosmic cathedral. Animators took the science even further, collaborating with astrophysicists to simulate the breakup frame by frame. One standout project, Fracture Point, used real gravitational stress models to choreograph the planet's demise. The result, a 4-minute short where the camera spirals through magma geysers erupting in slow motion, their trajectories precisely calculated from tidal force equations. The team even sonified seismic data, turning vibrations into a dissonant orchestra that crescendos as the core collapses. It's less a film and more a visceral physics lesson, one that went viral in both art and science circles. Musicians found inspiration in the silence of space itself. Ambient composer Yuichi Sakamoto created Debris Field, an album using frequencies converted from the debris cloud's radio emissions. The tracks pulse with metallic drones, simulated echoes of iron-rich fragments tumbling through the void, while intermittent chimes represent icy shards sublimating into gas. It's eerie, meditative, and oddly mournful, like a requiem for a world no one knew existed until it was gone. Even traditional media found fresh angles. Sculptor Lee Bull crafted a suspended installation from blown glass and ferrofluid, her work Event Horizon mimicking the moment gravity lost its grip. Visitors walk beneath jagged planetary fragments held mid-explosion, the fluid's magnetic tendrils illustrating invisible forces at play. The piece cleverly mirrors scientific visualizations of tidal shear, proving art doesn't just illustrate science, it can make it tactile. The most poignant responses came from generative AI artists who trained algorithms on telescope data to dream the planet's final moments. These surreal interpretations, one resembles a Van Gogh sky consumed by fractal cracks, reveal how technology bends our perception of cosmic events. They're not accurate nor meant to be. Instead, they ask, how does the universe feel when a world dies? This fusion of disciplines does more than entertain. It bridges the gap between empirical observation and human wonder. A scientist might calculate debris velocities, but an artist wonders what shadows those fragments cast on hypothetical moons. Together, they turn raw data into something that lingers, a reminder that even in destruction, there's beauty waiting to be framed. Out in the cosmic junkyard of shattered worlds, fragments drift like scattered treasure chests waiting to be opened. These aren't just geological curiosities, they're potential gold mines of rare minerals, metals, and even exotic materials forged under extreme pressures no factory could replicate. Picture a chunk of planetary core floating through space, its nickel-iron composition laced with platinum group metals that took billions of years to concentrate. Or a mantle fragment rich in rare earth elements vital for advanced electronics, liberated from kilometers deep crust where no drill could reach. The economic potential is staggering. A single metallic asteroid in our solar system is estimated to contain more platinum than has ever been mined on Earth. Now scale that up to planetary debris fields where fragments dwarf mountains. But cosmic mining isn't as simple as loading asteroids onto freighters. The logistics boggle the mind. How do you extract resources from objects hurtling through space at tens of thousands of kilometers per hour? Current concepts range from robotic space crabs that latch onto fragments to process materials on-site, to massive magnetic nets that capture metallic debris like a cosmic fishing trawl. Some proposals suggest nudging valuable fragments into stable orbits around moons or space stations, creating off-world mining colonies where zero gravity allows techniques impossible on Earth. Imagine smelting operations where molten metals naturally form perfect spheres without containers, or gas centrifuges separating isotopes with unprecedented efficiency in vacuum conditions. The ethical dilemmas run as deep as the technical challenges. Who owns the remains of a shattered planet? Current space law treats celestial resources as the common heritage of mankind, but legal gray areas multiply when dealing with debris from another star system. Would mining extinct worlds be seen as grave robbing on a cosmic scale, or pragmatic recycling of unused materials? Indigenous groups on Earth already protest asteroid mining as cultural appropriation of sacred celestial bodies. How much more contentious would it be to harvest fragments that might have once harbored life? Then there's the market paradox. Scarcity drives value, but cosmic resources could flood markets to the point of collapse. A single platinum-rich fragment might contain enough metal to render terrestrial mines obsolete, destabilizing economies built on mineral exports. Historians recall how Spanish silver from the New World triggered centuries of inflation. Now imagine that scenario playing out with interstellar commodities. Some economists propose treating space resources like Antarctica's mineral reserves, with extraction quotas to prevent economic shockwaves. Others argue that abundance should be embraced, allowing cheap access to materials that could revolutionize technology from energy storage to medical implants. The environmental calculus presents another layer of complexity. Space mining eliminates terrestrial pollution from digging pits and processing ore, but introduces new risks like accidental deflection of fragments into collision courses or contamination from extraterrestrial microbes. Early assessments suggest the carbon footprint of launching mining equipment could outweigh benefits unless done with renewable energy, a hurdle when most rockets still burn fossil fuels. Visionaries counter that space-based solar power or nuclear propulsion could eventually make the process carbon negative, especially if mined materials enable cleaner technologies back on Earth. Perhaps the most fascinating angle is how planetary debris could unlock materials science breakthroughs. Fragments from different layers, core, mantle, crust, offer a ready-made catalog of extreme condition alloys and mineral structures. Some might exhibit properties unknown on Earth, like metallic hydrogen stabilized by ancient pressures or carbon crystals with quantum characteristics. Laboratories could reverse engineer these materials to create everything from room temperature superconductors to ultra-strong construction composites. The shattered planet becomes less a source of raw materials and more a cosmic hardware store of prefabricated wonders. Looking ahead, the business models are as speculative as they are revolutionary. One startup concept involves debris mapping services, space versions of geological surveys that identify and appraise valuable fragments. Another pitches orbital refineries where multiple fragments are processed simultaneously, their product shipped via mass drivers to construction sites across the solar system. The most ambitious vision, using planetary debris as prefab components for massive space habitats, where entire city-sized chunks are hollowed out and repurposed rather than broken down. This isn't just futurism, it's the inevitable next step in resource utilization. Just as Earth civilizations progressed from flint nodules to iron mines to offshore oil rigs, our species will eventually look beyond terrestrial deposits. The shattered planet offers a glimpse into that future where catastrophe becomes opportunity on a cosmic scale. And while the challenges are immense, so too is the payoff, not just in wealth but in knowledge. Every fragment mined is a piece of a planetary puzzle, helping us understand not just how worlds die, but how we might one day live among the stars. When a planet shatters in the depths of space, it doesn't just send debris flying, it sends ripples through classrooms here on Earth. This astronomical spectacle has become a golden opportunity to ignite young minds. transforming abstract equations into visceral, unforgettable lessons. Take a typical physics problem about gravitational forces, dry on paper, but electrifying when framed as calculating the exact tidal stress that cracked a world in half. Teachers from Tokyo to Texas are using this event to bridge the gap between textbook theory and cosmic reality, proving that the universe's most violent phenomena make for its most compelling teaching tools. Hands-on activities bring the science to life. Some classrooms simulate tidal disruption with stretchy fabric and weighted spheres, letting students feel how gravity warps spacetime firsthand. Others track real debris data from telescopes, playing detective to reconstruct the planet's original mass and composition, a cosmic forensics lab with spreadsheets instead of scalpels. One inventive lesson has teams design survivor probes capable of enduring a planetary breakup, blending engineering with survival physics, the challenge. Protect instruments from flying magma shards and crushing pressures while harvesting energy from the chaos. It's Newton's laws meets post-apocalyptic sci-fi, and students eat it up. The interdisciplinary potential is staggering. Chemistry classes analyze spectral lines from the debris cloud to identify vaporized minerals, mirroring how astronomers hunt for extraterrestrial elements. Geography students compare the planet's fragmentation patterns to Earth's tectonic movements, discovering how scale changes everything. Even art classes get involved, creating scaled models of the debris field or animating the breakup in stop motion, because sometimes grasping the science starts with seeing the story. Digital tools amplify the learning. Planetarium software like Universe Sandbox lets students tweak variables. What if the planet had more iron, a closer orbit, and watch the destruction unfold in real-time simulations. Online collaborations connect classrooms worldwide to pool data, mimicking how real astronomers work across borders to decode cosmic mysteries. And virtual reality field trips, like those developed by NASA, a jet propulsion laboratory, drop students onto the planet's surface moments before fragmentation, turning abstract concepts into heart-pounding immersion. Beyond equations, this event teaches bigger lessons about scientific resilience. When initial observations didn't match existing models, astronomers had to adapt a masterclass in intellectual flexibility. Teachers highlight these moments to normalize failure as part of discovery, showing how every wrong answer refines the next question. Students learn that science isn't just memorizing facts, it's detective work where the universe keeps changing the clues. The most profound impact might be philosophical. Discussing a planet's demise inevitably leads to questions about Earth's fragility and humanity's place in the cosmos. One teacher in Norway frames it as a cosmic perspective shift. When your world feels small, remember, entire planets can vanish, yet the universe continues. Our problems matter, but so does our curiosity. That duality, humility, and wonder sticks with students long after grades are forgotten. What began as a distant catastrophe has become a catalyst, proving that the best education doesn't just inform, it transforms. Whether through equations, experiments, or existential awe, this shattered world reminds us that sometimes understanding how things fall apart is the first step to building something greater. And for the next generation of scientists staring at the stars, that lesson might be the most important of all. Watching a planet die isn't just an astronomical event, it's a mirror held up to our deepest existential fears. That distant world's violent end forces us to reckon with an uncomfortable truth. Earth, too, is temporary. The same cosmic forces that sculpt galaxies and birth stars don't discriminate. They'll eventually turn their attention to our pale blue dot. But this realization isn't meant to paralyze us with dread. It's an invitation to reframe how we view our place in the universe. Consider the perspective shift. For centuries, humans saw Earth as the unchanging center of creation. Now we know we're riding a speck of rock through a cosmos where worlds routinely form, flourish, and fracture like ice on a thawing lake. There's strange comfort in this cosmic impermanence. The shattered planet's demise reminds us that destruction isn't failure, it's part of a grand cycle. Stars die scattering elements that become new worlds. Planets shatter, leaving debris that may seed future life. Our own solar system bears scars of ancient violence. The moon born from Earth's collision with another world, Jupiter's gravity-hurling comets that delivered water to our young planet. Without catastrophe, we wouldn't exist. This duality, creation from destruction, runs through the universe like a golden thread, suggesting that even Earth's eventual fate might contribute to some future cosmic story we can't yet imagine. Yet the emotional weight lingers. Philosophers have grappled with mortality for millennia, but planetary death introduces a new dimension: collective impermanence. Individual lives are fleeting, but civilizations crave legacy, the hope that our monuments, memories, or microbes might outlast us. A dying planet shatters that illusion on a galactic scale. The fragments astronomers observed might drift for eons, but any cities, art, or DNA that world once held are now dust. This confronts us with an unsettling question. If entire worlds can vanish without a cosmic shrug, why do we assume humanity's mark will endure? Perhaps the answer lies in shifting our metrics of meaning. Traditional narratives prize longevity, pyramids standing for millennia, time capsules buried for future generations. But the universe operates differently. Brief phenomena, supernova, meteor showers, even mayflies can radiate intensity that dwarfs longer-lived counterparts. Applied to humanity, this suggests our significance might not hinge on lasting forever, but on burning brightly while we're here. The knowledge that Earth won't orbit forever could become liberating, an antidote to complacency, urging us to cherish and document our moment in the sun with unprecedented urgency. This perspective also reframes our current crises. Climate change and nuclear threats feel apocalyptic, yet against the backdrop of cosmic time, they're fleeting challenges, ones we're capable of overcoming if we channel the same ingenuity that lets us witness planets die across the void. The shattered world's fate shows what happens when celestial bodies lack agency. By contrast, we possess the rare ability to foresee dangers and adapt. In that sense, our awareness of cosmic fragility isn't a curse, it's a superpower. Ultimately, the lesson isn't about resignation to doom, but reverence for now. That distant planet's fragments will cool and darken, but for this fleeting moment, as starlight glints off their molten surfaces, they're part of a story witnessed by curious beings on a safe harbor world. Our tragedy would be squandering the cosmic luck that lets us watch, wonder, and weave meaning from the chaos. The universe doesn't care about survival, but it has against impossible odds produced minds that do. However long Earth lasts, that alone makes us extraordinary. Hollywood loves a good planet destroying spectacle Death Stars, vaporizing worlds in an instant, asteroids hitting Earth with apocalyptic force, or black holes swallowing planets whole. But the reality of planetary destruction is far stranger and more nuanced than blockbuster special effects suggest. One of the biggest myths, that planets explode like overinflated balloons. In truth, most planetary demises are slower, messier affairs governed by gravity's relentless tug rather than sudden combustion. Take tidal disruption, the process that shattered the planet we've been discussing. This wasn't a fiery explosion, but a drawn-out unraveling where gravity stretched the world like taffy until its very structure failed. The energy release was immense, but it happened over years, even decades, more like a bridge collapsing under stress than a bomb detonating. Another common misconception is that collisions between planets are chaotic, random events. While cosmic crashes do happen, they're rarely the catastrophic free-for-alls depicted in movies. Physics imposes order even in chaos. When two worlds collide, their trajectories and angles determine whether they merge, shatter, or glance off each other. The Moon's birth from Earth's collision with a Mars-sized object wasn't a haphazard impact. It was a precise strike at the right angle and speed to launch debris into orbit, where it coalesced into our lunar companion. Even in violence, the universe follows rules. Then there's the myth of instant annihilation. Pop culture often portrays planetary death as a single, dramatic moment, a crack racing across a world's surface before it bursts apart. Reality is less theatrical. A planet's crust might fracture gradually, its mantle oozing through widening fissures like lava through ice. Atmospheric loss could take millennia, with gases bleeding into space molecule by molecule. Even the infamous planet-killer asteroids don't obliterate worlds in one strike. They trigger cascading disasters, earthquakes, volcanic winters, and atmospheric changes that unfold over generations. The dinosaur-killing Chicxulub impact didn't vaporize Earth. It altered the climate just enough to tip ecosystems into collapse. Perhaps the most persistent fantasy is that advanced civilizations could weaponize planetary destruction. While sci-fi loves its planet-busting superweapons, the energy required to truly annihilate a world defies practicality. Consider this: to overcome Earth's gravitational binding energy, the force holding it together, you'd need to deliver 30 trillion megatons of TNT equivalent. That's 1,000,000 times humanity's total nuclear arsenal. Even if possible, the sheer inefficiency makes it absurd when simpler weapons could achieve the same strategic goals. Nature, with its black holes and rogue stars, will always be the universe's most formidable demolition expert. The final myth worth debunking, that planetary destruction is always tragic. From a cosmic perspective, it's just another phase in an endless cycle. Shattered worlds become asteroid belts or raw material for new planets. Dying stars forge heavy elements that seed future life. Our own solar system likely contains remnants of long-vanished worlds, their fragments now part of Earth's bedrock or floating in the Kuiper belt. Destruction isn't an end, it's a transformation, proving that in the grand scheme, nothing is truly lost. Just recycled, understanding these truths doesn't diminish the awe of cosmic violence, it deepens it. Real planetary death isn't about flashy explosions or villainous superweapons. It's about the slow, majestic interplay of forces that have shaped the universe for billions of years, and that's a story far more compelling than any fiction. The universe has shown us its capacity for planetary destruction, but this is just the opening act in a cosmic drama brimming with unexplained phenomena. Beyond shattered worlds, astronomers are chasing clues to even stranger possibilities lurking in the darkness. One tantalizing frontier: rogue planets, worlds untethered from any star, drifting through interstellar space like cosmic nomads. Current estimates suggest there could be billions of these free-floating orphans in our galaxy alone, ejected from their birth systems by gravitational chaos. Some might retain heat from their formation or radioactive decay, harboring subsurface oceans that persist for eons despite the freezing void. The upcoming Nancy Grace Roman Space Telescope could detect these dark wanderers through microlensing, capturing the subtle way their gravity bends light from distant stars. Imagine a planet-sized version of Earth, frozen solid yet carrying the chemical seeds of life, sailing silently between the stars. It's not science fiction, it's a reality we may soon confirm. Then there's the enigma of dark matter's role in planetary systems. We know this invisible substance outweighs normal matter 5 to 1, but could it clump densely enough to influence individual worlds? Theoretical models suggest certain regions of galaxies might harbor dark matter hurricanes, rivers of particles streaming through space at incredible speeds. If a planet orbited through such a current, the cumulative gravitational nudges might subtly alter its trajectory over millennia. Even more speculative is the idea of dark planets, hypothetical objects made entirely of dark matter, undetectable except through their gravitational whispers. While no direct evidence exists yet, future gravitational wave detectors could potentially catch the ripple of two such shadow worlds colliding in the void. The hunt continues for destruction mechanisms beyond tidal forces. Some theorists propose quasar erosion, or where the intense radiation from a galaxy's supermassive black hole could strip away a planet's atmosphere molecule by molecule over billions of years. Others study the potential for vacuum decay, a catastrophic scenario where a bubble of unstable spacetime expands at light speed, rewriting the fundamental laws of physics in its wake. While purely hypothetical, these ideas push our understanding of how extreme the cosmos can get. Even more unsettling are mathematical models suggesting certain high-energy particle collisions could, under specific conditions, trigger microscopic black holes capable of consuming a planet from within. The odds are astronomically low, but in a universe this vast, even the improbable demands consideration. New classes of celestial violence may await discovery in binary star systems. Imagine a planet trapped between two dancing stars, subjected to alternating gravitational pulls that stretch its structure in ever-shifting directions. Recent simulations show these worlds could experience resonant fracturing, where tidal forces align at precise intervals to amplify stress exponentially. The result, a planet that doesn't just crack, but pulverizes rhythmically like a drumhead hit with perfect timing. Upcoming missions like the European Space Agency's Plato telescope are specifically designed to monitor these complex systems, potentially catching the first evidence of this bizarre demise in action. Perhaps the greatest mystery lies in what we can't yet imagine. Every few years, astronomers stumble upon phenomena that defy existing categories, like Oumuamua, the interstellar visitor with its peculiar acceleration, or the bizarre planetesimal, found orbiting a white dwarf seemingly made of metallic chunks from a shattered core world. Each discovery hints at processes we haven't begun to theorize. The next breakthrough might come from monitoring neutron stars, whose unimaginable density could shred passing planets into spaghetti-like streams of plasma. Or from watching young solar systems, where protoplanets still glowing from formation might collide in spectacular mergers we've never witnessed. What makes this search so electrifying isn't just the potential for new knowledge, it's the humbling reminder of how much remains hidden. For every cosmic catastrophe we've observed, there could be 10 more lurking in the shadows, each with its own physics-defying signature. The universe doesn't operate on human scales or timelines. It's a laboratory where forces we can barely comprehend play out over eons. And as our telescopes grow more powerful, our simulations more precise, we're not just passive observers, we're detectives piecing together clues to the greatest mysteries of all. The Shattered Planet was just the first chapter. The cosmic encyclopedia of destruction has many pages left to turn. The day astronomers witnessed a planet crack like glass wasn't just a scientific milestone. It was a cosmic wake-up call, revealing how much we still have to learn about the forces that shape our universe. This event shattered more than just a distant world. It fractured our assumptions about planetary durability, proving that even the most massive objects in space have breaking points. The real revelation lies not in the destruction itself, but in what it teaches us about resilience, transformation, and the delicate balance that keeps our own world intact. Think about the sheer improbability of this discovery. In the vastness of space and time, we happen to be looking in the right direction with the right tools at the precise moment when gravitational forces pushed a world beyond its limits. That alignment feels less like coincidence and more like the universe offering us a front-row seat to its most dramatic performances. And what a performance it was, a celestial ballet where gravity played both choreographer and executioner, stretching the planet until its very structure surrendered. The lessons extend far beyond astrophysics. Watching a planet's demise reminds us that cosmic violence isn't just destructive, it's creative. The same forces that tore this world apart are responsible for forging new ones, scattering elements that might one day coalesce into future planets or even life. Our entire solar system likely contains fragments of similar cataclysms from billions of years ago, meaning we're literally made from the debris of ancient cosmic collisions. There's poetry in that cycle, a reminder that endings in the universe are often beginnings in disguise. For all our technological prowess, events like this keep us humble. No supercomputer could have perfectly predicted how this planet would fracture, just as no telescope could have prepared us for the haunting beauty of its debris field glowing against the void. These moments expose the limits of our models and the boundless creativity of nature, which continues to surprise us at every turn. As we push deeper into the cosmos with ever more powerful instruments, one truth becomes clear: for every mystery we solve, a dozen new questions emerge. The Shattered Planet isn't the finale, it's the opening act in a much grander exploration of how worlds live and die. Upcoming telescopes will hunt for similar events, probing the extremes where planetary physics meets its match. Who knows what other extraordinary phenomena await discovery? Perhaps we'll witness a moon torn apart by tidal forces, or catch the birth pangs of a new world forming from the ashes of an old one. This is why we explore, not just to catalogue the universe, but to understand our place within it. Every shattered world, every cosmic collision, every fragile balance of forces reminds us that Earth's stability is a precious anomaly in a universe of constant change. So the next time you look up at the night sky, remember, those distant points of light aren't just scenery. They're stories waiting to be told, each one more incredible than the last. If this journey through cosmic destruction and rebirth has sparked your curiosity, you're not alone. The universe invites us all to be lifelong learners, to question and to wonder. Share your thoughts in the comments. What cosmic mystery fascinates you most? And don't forget to like and subscribe for more deep dives into the wonders of space. The cosmos has countless stories left to tell, and we'll be here to bring them to you, one mind-blowing discovery at a time.